Okay, to make this go a bit smoother, I'm going to add an assumption here. Okay, I'll assume all the vectors are 0, just to make it a bit smoother later on. Okay, I'll start by taking my two projections and writing them down in equality with each other. And then I'm going to work out what this means. So I'll start by moving the second projection over to the left. And what do you get? Well, you get u dot v over v dot v and w dot v over v dot v. And I'm going to go ahead and factor out that v. Okay, so I brought this over, and then I factored out this v here. And here I am. Now I'm going to do even more factoring, because inside the bracket I have a v here and a v here. And what can you do? Well, you can make some big brackets. You get u over v dot v minus w over v dot v all dot v. And then as a scalar multiple of the vector v. This equals a 0 vector still. So almost there. I have this common denominator. So why don't I move that out? V dot v. And I got u minus w in the bracket dot v times, as a scalar multiple, v equal to 0 vector. Okay, now I'm trying to prove that, well, I'm going to try and prove that something is perpendicular. Well, what is perpendicular? I want to prove that u minus w is perpendicular to v. So you can see, I hope, is that I want to argue that this rectangle is 0. I want to argue that this rectangle is 0. Well, I'm just going to have to use my assumption here to make that argument. Okay, I'll say, well, you have a scalar multiple of a non-zero vector. So the scalar multiple must be 0. So this is equal to the real number 0. And then you say, well, this is not 0 because it equals the length of v squared. And v is non-zero, so its length is non-zero. So therefore, u minus w dot v is 0. And these are non-zero vectors, so therefore u minus w is perpendicular sign to v.